Solving linear systems and computing top eigenvalues and eigenvectors are fundamental tasks with numerous applications to machine learning and throughout computer science more generally. For this reason, optimal algorithms for these problems are extremely important. Focusing just on linear regression for now, there are several well-known approaches for solving this problem, which can generally be split into two categories. On the one hand, we have first-order methods such as conjugate gradient descent or accelerated gradient descent. Conjugate gradient descent enjoys three different kinds of guarantees. A low accuracy guarantee, which depends just on epsilon, which is the squared L2 error. A condition number dependent guarantee, which scales with the ratio of the largest and smallest eigenvalues of A transpose A. And a dimension dependent guarantee, which ensures convergence to the exact solution after d iterations, at least assuming infinite precision. In contrast to first-order methods, we can also solve this problem by directly inverting A transpose A. We can do this either through naive methods like Gaussian elimination, or through more sophisticated methods like the Strassen algorithm, which requires time only d to the omega, for omega which is currently around 2.37. Now, comparing these approaches, we see that a key advantage of first-order methods is that each iteration requires only computing the gradient, that is, a single matrix vector product. And the runtime of these methods can therefore be improved quite significantly when the matrix A transpose A is sparse. Now, this property is not shared by matrix inversion-based methods, since the inverse of a sparse matrix may itself be dense. Furthermore, even for non-sparse matrices, these first-order methods can still be much faster than matrix inversion approaches when the dimension is high, or as long as the data is well conditioned or the desired accuracy is low enough. For this reason, we look to first-order methods for solving least squares or linear regression and ask whether further improvement is possible. I should note that I've focused here on linear regression, but the picture is quite similar for the case of computing top eigenvalues or eigenvectors. On the one hand, there are first-order methods like the Lanczos method, whose runtime depends on the number of non-zeros and also there are matrix inversion-based methods whose runtimes do not. So we would also like to know whether faster first-order methods are possible here. Back to linear regression, it's instructive to see what sorts of improvements we might be able to hope for. So we'd like a first-order method so that we can scale to high dimensions, and we'd also like its runtime to be independent of the condition number kappa so that we can accommodate poorly conditioned data. The current state of the art here is conjugate gradient descent, which requires either 1 over square root of epsilon or d iterations, depending on the desired level of accuracy. In prior work, Simchowitz showed that the 1 over square root of epsilon rate can't be improved in a low accuracy regime when the desired error epsilon is larger than 1 over poly d. But this result is nothing to say for a high accuracy regime, and it does not show that the dimension-dependent bound is tight. We therefore ask how many iterations are needed when a high accuracy solution is desired, specifically when the error epsilon is smaller than 1 over poly d. Perhaps there's a method with only logarithmic dependence on the error, or even just a logarithmic dependence on the error and a sublinear dimension dependence. Unfortunately, our work shows that no such improvement is possible using first-order methods. Now, to state our lower bound, we consider a matrix vector product oracle. The algorithm is allowed to choose an adaptive sequence of vectors x, and it will receive back the product m times x for the eigenvalue objective and A transpose AX for the least squares objective. And for the least squares objective, we will allow the algorithm to just know the B vector directly. The question now is how many oracle queries of this type are needed in order to approximate the top eigenvalue of m to accuracy epsilon, or to compute a solution ax equals b to L2 error epsilon. The answer to this question kind of exactly indicates the limits of first-order methods for eigenvalue or least squares computation. Our main result is the following. Any method for computing the top eigenvalue, top eigenvector, or least squares solution to error less than 1 over d squared must query the matrix vector product oracle at least order d times. For least squares, of course, this ignores a logarithmic factor. Therefore, for least squares, conjugate gradient descent's d iteration complexity is optimal up to log factors for high accuracy solutions, and it cannot be improved. A key feature of a lower bound is that they hold even for arbitrary randomized algorithms, and they require no assumption at all about the algorithms other than requiring that they only access the objective through a matrix vector product oracle. This is important since for many problems, randomized methods can substantially improve over deterministic ones. So having lower bounds which work against randomized methods gives a sort of more comprehensive result. I will now briefly outline our proof, which is based on a simple construction that may be of interest more generally. We begin by proving a lower bound for computing the top eigenvalue, and then proceed to show that this implies a lower bound for solving linear systems via a reduction. The lower bound for computing top eigenvalues is quite simple and is based on a Wishart matrix, with W equals XX transpose, where the entries of X are IID Gaussian. We then construct the hard instance as a function of W, and this together forms a very simple distribution over positive definite matrices, and it seems like it should be a very benign instance. But nevertheless, this is the basis of our lower bound, and we show that it's actually quite hard. And I want to note that by constructing the matrix in this way, we've sort of flipped it around, and we will, rather than showing that the top eigenvalue of M is hard to find, we will show that the smallest eigenvalue of W is hard to approximate, and these are essentially equivalent. So first, we observe that for any sequence of queries, we can assume without loss of generality that the queries are orthonormal. This is because any non-orthogonal components of the queries could be computed based on previous oracle responses, and the scaling of the queries does not really affect the amount of information gained. Next, the key step is to show that for any sequence of k orthonormal queries, there is a component of W, which will denote W tilde k, which is completely independent of the first k oracle queries and responses. And therefore, this component W tilde k is sort of completely unknown to the algorithm. We prove this by constructing a rotation Vk, for which a component of the bottom right d minus k by d minus k submatrix has a Wishart distribution, even when conditioned on the first k queries and the responses from the oracle. And this is basically a consequence of the fact that orthogonal components of Gaussians are independent. Finally, we show that this unknown component of the matrix is quite important. Specifically, the smallest eigenvalue of VWV transpose is upper bounded by the smallest eigenvalue of W tilde. Since V is a rotation matrix, this means that the smallest eigenvalue of W is also upper bounded by the smallest eigenvalue of W tilde. And now, using properties of the Wishart distribution, we can therefore show that the smallest eigenvalue of W cannot be approximated to accuracy higher than 1 over d squared until the number of queries is of order d. And this completes the lower bound for computing the bottom eigenvalue, which again implies a lower bound for computing top eigenvalues and also for eigenvectors. To extend this lower bound to solving linear systems, we use a standard reduction based on what is called shift and invert preconditioning. This was studied by Saad and Garber et al. The reduction works as follows. First, we observe that for a scalar lambda larger than the top eigenvalue of m, calculating the top eigenvalue of lambda I minus m inverse is enough to compute the top eigenvalue of m. In addition, for lambda close to the top eigenvalue of m, the matrix lambda I minus m inverse has a constant eigengap. That is, the difference between the first and second eigenvalues of m is fairly large, and this implies that the power method will very quickly converge for this matrix. And I'll also point out that a close enough estimate for this to be true of the top eigenvalue of m can be obtained using binary search. Finally, we note that implementing the power method for this matrix requires solving just a single least squares problem per iteration, And since there are only a logarithmic number of iterations necessary for the power method, this means that if you could solve least squares quickly, you could compute top eigenvalues quickly too. And in light of our previous lower bound for computing top eigenvalues, this implies a lower bound on how fast you can solve least squares problems. We can also extend these proofs to depend on the sparsity level of the matrices in question. Specifically for S squared sparse matrices, we can show an order S lower bound for computing eigenvalues and eigenvectors, and an omega tilde of S lower bound for solving linear systems. So in total, we showed lower bounds for computing top eigenvalues and eigenvectors, and also for solving linear systems, which indicate that computing high accuracy solutions requires at least D matrix vector products for dense matrices, or square root of the sparsity matrix vector products for sparse matrices. These lower bounds are information theoretic, and they apply to any randomized algorithm. And they're also based on a very simple construction using the Wishart distribution over positive semi-definite matrices. We view the simplicity of our proofs as a great strength, particularly as compared to previous lower bounds for least squares and eigenvalue computation, such as those by Simchowitz 2018, and also as compared with previous lower bounds which hold up against randomized algorithms, which typically require much more complicated constructions and also more delicate arguments. Thank you for watching.